Okay, so the next challenge problem that we're going to do is probably a little bit more deceptive in terms of it tricks you into thinking that you can actually use by parts on it, but you can't, okay? By parts is a formula you can't actually use on this function, and there's a reason why, okay? Well, because we know that when we're integrating by parts, we have u prime v is equal to uv minus integral of uv prime, right? This is the formula for by parts. Now, the problem is, what do you set as your u prime and what do you set as your v? Because if you set u prime as sine inverse of x, right? Well, what is the integral of sine inverse of x to find u? Well, you don't know, right? Because that's a pretty complex question on its own. And if you set u prime as x, well, obviously you can figure out u, that's a half x squared, but then when you put in v prime, and you know v is equal to sine inverse of x, and you can find v prime too, right? That's 1 over square root of 1 minus x squared. So this all works, but what happens when you take these two and multiply them together and plug it into this, right? So you have integral of, well, I'll take the constant out for argument's sake, x squared on square root of 1 minus x squared. Now this, again, is a really, really difficult problem itself, and it's not as apparent how you do this, okay? So there's actually a trick like we used in challenge problem 1, the exact same trick, and the trick is realize that sine inverse of x is an angle, right? So what we're going to do is we're going to start by letting theta equal sine inverse of x. Okay, now we're here. So therefore, if I take a sine on both sides, I have sine theta is equal to sine of sine inverse of x, right? And we all know f inverse of f of x is just equal to x. So same thing here, because sine is a function, right? So this is sine theta is equal to x, right? So from this, now we can make direct substitutions into this. But obviously we also need to make a substitution for dx. So what are we going to do? We're going to take the derivative of this function. So therefore dx is equal to cos theta, right? So when dx is equal to cos theta, we can make the direct substitutions now. So we have, and by the way, I got dx is equal to cos theta by taking the derivative on both sides of this function, right? So now we just substitute everything in. So we know that x is sine theta, so we have integral of sine theta because x is sine theta. Now sine inverse of x is theta, so times theta, and then dx is cos theta d theta. Okay. So at this point, we now have the integral of theta sine theta cos theta d theta. Now, for the people who have a sharper eye, they'll realize this is almost a double angle. So the only thing it's missing is a 2, because we know sine 2 theta is equal to 2 sine theta cos theta. So dividing both sides by 2, I get a half of sine 2 theta is equal to sine theta cos theta. So now I can make a direct substitution. I can change sine theta cos theta for a half of sine 2 theta. So now my integral starts becoming a little bit nicer. This is an integral of theta times by a half of sine 2 theta d theta. So now it looks pretty clean. Now we can take the constant out the front so it doesn't get in our way. And we're left with this integral. And this integral is actually pretty easy because now it's just a standard by parts, isn't it? So again, we will say integral of u prime v is equal to uv minus uv prime. So in this, what are we going to set as our u? What are we going to set as our v? Well, it's quite apparent, okay? U prime is 100% going to be sine 2 theta. And v is 100% going to be theta. So integrating this by using our integration laws, we get u is equal to the integral of sine 2 theta, which is equal to minus a half of cos 2 theta. Because remember, you have to take the inverse of this and multiply it, right? And v prime is going to be, well, 1, right? Because derivative of theta is 1 when we're taking derivatives with respect to theta, right? So now what we can do is we can plug this in the by parts formula. So integral, or a half the integral of theta, so theta sine 2 theta, is equal to, well, a half, because remember, we're always, if this is a half here, then there must be a half here, right? A half the uv, so u in this case is half cos theta minus a half cos theta, and v is theta. So it's minus a half theta cos 2 theta minus the integral of uv prime. Well, u is minus a half cos 2 theta, and v prime is 1, and then we're integrating with respect to theta. So now we have a half of minus a half theta cos 2 theta, and obviously, sorry, this is a minus, I should make this more clear, right? So this minus and this minus will cancel, and we're then left with a plus, and then we'll take the constant of a half at the end. So we're left with a half cos 2 theta d theta. So now, at this point, it's pretty apparent, it's pretty easy now. So we get a minus a half theta cos 2 theta plus 1 half, and the integral of cos theta is obviously a half of sine 2 theta. And then we just chuck the plus c on at the end, right? So now, if we expand everything out, we get minus 1/4, because we're multiplying this a half, theta cos 2 theta, plus now a half times a half times a half is 1/8. 1/8 of sine 2 theta, okay, plus c. Okay, well, this now looks a little bit more solvable, okay? So now remember, we're trying to find this with respect to x, this integral with respect to x. So again, we can't actually leave it like this. So we have to change this all. So we said initially theta is equal to sine inverse of x. So we can make that direct substitution. So minus 1/4 sine inverse of x, and then we have cos 2 theta plus 1/8 of sine 2 theta plus c. So now, how do we deal with our double angles? Well, what we do is we use our double angle properties. So by our double angle properties, we know that cos 2 theta is equal to 1 minus 2 sine squared theta, and we know sine 2 theta is equal to 2 sine theta cos theta. So taking these two double angle properties into account, we can make a direct substitution, right? So cos 2 theta becomes 1 minus 2 sine squared theta, plus now 1/8 of sine 2 theta becomes 1/8 of multiplied by 2 sine theta cos theta plus c, right? So now we're at this point where it looks doable, right? We have everything in terms of sine theta and cos theta and sine squared theta, which is all the stuff that we actually know. So now what we can do is we can finally make our remaining substitutions. Now, sine squared theta, right? Well, if we said that x is equal to sine theta, then x squared, by squaring both sides, is sine squared theta, right? So we can just change sine squared theta for x squared. So it's minus 2x squared plus 1 on 8, and 2 and 1 on 8 cancels to 1 on 4. And then we know sine theta is x. And now what is cos theta? So using the same strategy of the triangle from last challenge problem, right? I highly recommend you watch that too. We know that sine theta is equal to x on 1, which is equal to opposite over hypotenuse, right? So from here, we know that if this is theta, then the opposite angle is x and the hypotenuse is 1. So using Pythagoras theorem, we can get square root of 1 minus x squared here. So therefore, cos theta is equal to the square root of 1 minus x squared on 1, which is the square root of 1 minus x squared, okay? So now we're at this point, right? We know what cos theta is, so again, we can make a direct substitution. And that becomes square root of 1 minus x squared plus c. And that right there is our final answer for this second challenge problem. And this one is about the same difficulty as the first one, so they're not too difficult. But later down the line, at challenge problem 3 and 4, they're starting to get a little bit more tough.